name is Todd Majeski, and I'm the local WA president here of ASEG here sitting in Perth right now. And welcome to our continuing webinar series. This one I'm hosting is by Dr. Avseth, and his talk is on basin-wide and multi-scenario modeling of rock properties and AVO feasibility biomes. Now, before we get right to him, though, you'll have to listen to me talk a bit. And so the first thing I want to do is thank our corporate members. They're very important to us because without these, we wouldn't have this presentation, for instance, going on right now. So our corporate plus members, High Size, Total Seismic, and Bell Science are big supporters, as are corporate members who are Southern Geoscience, Santos, Transparent Earth Geophysics, and Doug. So thanks to all of them. Really appreciate that. Then locally in the different states, we've got a bunch of other smaller brand sponsors that are also very important. They help us locally. I don't have time to go through all the ones that you can see here for WA, which is unfortunate, but there's also quite a few in SA and NT and also New South Wales. So with all of those, they really do a lot of help, and a lot of our things that we do are directly from their donations. And for those of you who have not been to one of our webinars, we're not going to let you just shout out questions throughout the talk. You'll have to type them in below. You'll see if you look at your screen, move your mouse, you'll see the Q&A. Just type them in, and then at the end of the talk, then we'll try to go through all of them, or at least as many as Per can go through at the time that we see. Okay, so there's that. Now, like I was saying, this is a webinar series, and we have actually there's a few more than this, but we've got some upcoming webinars real quick. So one of them's tomorrow, actually, at 4 p.m. Perth time, which is the important time, of course. And that's by Christopher Bonso. And he's going to be talking about the influence of dynamic topography, climate, and tectonics on the Nile River source sink system, which sounds pretty cool. Next Thursday at noon Perth time, WA is going to be hosting Dr. Subhaji Bhattacharya, and his talk sounds pretty cool too. Actually, this one sounds really cool. Time series clustering and class-based machine learning and predicting elastic properties of rocks. Why, how, what, and so what. So we'll see how that goes next week. In the meantime, there are a lot more than just, those benefits aren't just, we've got a pretty good technical journal that we put out called Exploration Geophysics. And we've got research and case studies, not just from Australia, but from around the world. And it's a good magazine to read. And we do have our own bi-monthly chat rag called Preview, which kind of covers the local exploration geophysics, within Australia. And again, we do have our conferences, so that you would have a reduced entry to our upcoming AGC conference, if you remember. And kind of unusual, you'll have free entry to our typical technical events in the state. I'd say typical because, well, nowadays with COVID, you can't guarantee any of these actually going to happen, but at least they're there. You have access to job advertisements, and we have a pretty good annual wine offer. Every year it's coming up pretty soon. We have a good deal on very good wine. And of course, there's social events in your state. Like, for instance, next week we'll have a lawn bowling social night coming up in kind of Greater Perth. And again, this is a nice place to do networking for professional and other ones. And we offer research funding and travel scholarships for students. And in WA, for instance, we've got 4 deserving students, and they are going to be going off to the AGC because of ASEG, which is pretty nice. And what's also unusual, I think, about our society is we offer free membership for students. And that, I think, that's pretty unusual, and half price for retirees and recent grads. Okay, and then in terms of how we keep in touch, well, yeah, you've hopefully been receiving the monthly newsletters, and we have a website. We're on Facebook, we're on Twitter, we've got our own LinkedIn page, and we've also got a YouTube page where we harbor all these different webinar videos and sometimes some of the coursework if it's allowed by the presenter, in which case, for instance, this one will be out there very soon, and there's no special password you need or things like that. So it's open because that's the way ASEG works. I think that's pretty cool. So now I'm pretty much ready to shut up and pass the baton to Per, but I want to go through his bio with you. So here's a slide for that. You can read along with me. So Per is a geophysical advisor and the CTO of Dig Science in Oslo, Norway, and a part-time researcher at the Department of Electronic Systems at Norwegian University of Science and Technology, NTNU, in Trondheim. Per received his master's in applied petroleum geosciences from NTNU in '94, and he's got a PhD in geophysics from Stanford in 2000. He worked as a research geophysicist at Norsk Hydro in Bergen, Norway, in 2001 to 2006. He was a consultant at Rock Physics Technology in 2006 to 8, Odin Petroleum from 2008 to 2012 in Bergen, and was a geophysical advisor in Tullow Oil in Oslo from 2012 to 16. He's held a position as an adjunct professor in reservoir geophysics at the Department of Petroleum and Geoscience in NTNU from 2008 to 2020. Yeah, he's been a busy guy. And Per was also the SEG honorary lecturer for Europe in 2009. He's a co-author on a book called Quantitative Seismic Interpretation, and he's published extensively in the field of rock physics and AVO analysis. And besides this, I can say if you were around Perth in 2015, I think is the year, you might have taken his rock physics SEG course like I did back then. And so he should be, pretty well known around here. So with that, I'm finally going to shut up and I'll pass this over to Per. So let's go here and
thank you, Todd.
Yeah.
Let's see, I just shared this screen. You should be back. I guess you see my screen.
Perfect.
Good. Okay, thank you for that introduction, Todd, and hello everybody. And I'm very happy to be back in Western Australia, this time virtually though. So the title of the talk today is Basin-wide and multi-scenario modeling of rock property and AVO visibility volumes. Let me just start with a brief outline. So first I will just show you what I refer to as the rock physics link. Then I'm going to motivate the problem that I'm going to look into during this specific talk. And the topic is really going to be on combining rock physics with compaction modeling. Then I'm going to demonstrate some multi-scenario rock physics and AVO visibility modeling with examples from the Glittener field. It's a field that I've been working on for many years and also been used extensively also in the book that I published all the way back in 2005. So I'm going to look a little bit back into that today. Then I'm going to move to the Barents Sea, where there are extensive tectonic uplifts, and we need to account for those also when we make these AVO visibility maps. So I'm going to show you some examples of that. And finally, I will summarize. Okay, so let me first start with this rock physics link. And the way I define rock physics is really the bridge of the link between your geophysical observables and your geology or your geological knowledge. And of course, there are some challenges bridging these two. And on the geological side, the problem is often that we have very many parameters. The geology is often complex, and there are ambiguities and variabilities. On the other hand, on the geophysical side, we actually more often suffer from having limited observables. There could be noise and artifacts and also scale and resolution issues. So sometimes this rock physics bridge is almost like a bottleneck as well, because we really need to constrain or know a lot of geology before you even start to predict something from the seismic. In any case, by having this bridge, it is essential to do that when we perform what we refer to as quantitative seismic interpretation or quantitative interpretation. But of course, then we need to bring along the uncertainties, be aware of the errors and the pitfalls. So this is just sort of the rock physics course in one slide. So let's move on and see how this can apply to this case. And I bring you over to the key motivation for today's talk. And this is a cartoon or a schematic section, geological section. It could be in the Barents Sea. It could also be offshore Norway in the North Sea, where you have rotative fault blocks, quite complex geology, and then you have Cretaceous and Tertiary filling in. And let's assume you have drilled one of these structural fault blocks and discovered some hydrocarbons. And this is an issue that we face quite often, both in frontier exploration, but also now these days when we're trying to look for more subtle traps away from the structures. And the question is really, how do we extrapolate? How do we know how the rock properties change? One thing is to understand how the geology is changing. Usually the geologists, based on a conventional interpretation of stratigraphy and structures, have a fairly good idea of where they expect the sands to be present. What about the elastic properties of these sands? And that's really critical when it comes to say something about the expected seismic signatures and the AVO responses in particular. And of course, it could also be some interesting updip prospects in another fault block that has been experiencing different burial history. So at the end of the day, what I'll really demonstrate today is how important it is to link the burial and compaction history with the rock physics to better understand what we see in the seismic data. I can also use this as a t-shirt slide to demonstrate this. And to the right is a seismic section offshore northern North Sea. There is a well that has been drilled. It's actually a Gjøa discovery well. It's a Jurassic structure that has been drilled. But let's assume now we look at the seismic and you can see some interesting seismic anomalies updip within the Cretaceous layer. And the question is then, can we say something about what is this an expected response to see something brightening up, for example, due to hydrocarbons, or could it just be because of some lithology effect? And then we really need to understand the burial history, and I just added 2 burial curves to the left here, one for the well, and you see you have from early Cretaceous continuous subsidence, and then in Cenozoic there has been some uplift, and then you see that it actually has been deeper than 70 degrees centigrade, and that's a critical temperature where you start cementing the rock. So you go from a loose sediment to a rock, and you lithify it. So these Cretaceous sands here at this well location would then be relatively stiff because of this presence of quartz cement. We can actually model this, and that's what I'm going to show you later, is that we use something called the Valderhaug model to model the quartz cementation as a function of time and temperature, and combining that with the rock physics, we can say something about the expected rock physics properties here. But what then about this green, what's inside the green circle here? Let's call it the prospect. And you see here that the burial history is different, and you can actually see in the stratigraphy here that there has been some uplift increasing towards Norway. The coast will be on the eastern side or right-hand side, and you see that it's the uplift has been larger than more basinwards. And that's what you see also in the burial curve here. And it could be that this prospect was never really into this, what I often call the frying pan. It wasn't spending enough time into this high enough temperature to really consolidate. So just over these short distances, if you have big tectonic differences, you can really have big changes in the rock properties just as a function of your diagenesis and your burial history, and not only based on the fluid. Okay, and this was published, this kind of methodology was published in a leading edge paper 5 years ago, together with my colleague Ivan Lehosky in the leading edge. And here is just to summarize it without going into details of the equations, just show the workflow. So if you have the burial history, and this is an example, here it says stir formation. So this is a Jurassic sandstone, and this is typically what you see in the Barents Sea, which I'll get back to later. And you see that it was deposited maybe around 200 million years ago, and then it was buried deeper and deeper, and at some point you get onset of quartz cement because the temperatures are high enough. But then more recent, it was uplifted quite drastically, and today it's just a few hundred meters under the seafloor in some places. But of course, the properties remember the history. So rocks have memory, I like to say. And this diagenetic modeling using the Valderhaug model, there are different approaches, but one is the Valderhaug. And the Valderhaug model quantifies the quartz cement volume as a function of this burial history. And it's a function of, it's an integral over time and temperature. Other important input parameters are the grain size, and you can put in clay coating as a parameter, and so on. And especially the grain size is important because it defines the specific surface area available for quartz cement. You see here that the cement volume is increasing both on the way down and during the uplift phase, as long as the temperatures are high enough, meaning above around 70 degrees. And then it's kind of staying constant when it's getting colder again. This cement volume will, of course, affect the porosity burial trends or porosity depth trends as well. So here you see the porosity evolution from deposition with depth during burial and during the uplift phase. And then we have, having this porosities and cement volume from the diagenetic modeling, we can plug these into our rock physics models and use these contact theory models, Hertz-Mindlen and Dworkin-Nur contact theory models combined with Hassen-Strickman, and we can just plug in from the burial-driven cement volume and porosity into the rock physics model, and we can actually predict these rock properties as a function of the same burial history. And you see here from the position, you increase your impedance, and then you have a more dramatic increase as you start to cement the rock, and then during the uplift. And you also see the difference between, here is just an example, between brine and oil. Quite a good fluid sensitivity in the beginning, but as you start to cement the rock, your fluid sensitivity is drastically decreasing. And today, even though you're quite shallow, your fluid sensitivity is quite small because of the cemented nature of the rock. We can also model how the shale is experiencing this burial history. It's a little bit more complicated to do that with physical models. Very often we have enough wells to quantify the shale compaction trends empirically from well logs, because maybe 70–80% of the subsurface are shales. So it's more easy to do the shales data-driven, where the sands, especially if you have few wells, we really need to go model-driven for the sandstones. But then having the shales and the sandstone together, we can actually model the AVO. And here's just a cross plot of intercept and gradient. With the dashed here is the background trend, the shale background trend, and you see the brine and oil signature is expected to change as a function of burial here for a given case. Okay. This methodology was further developed and published recently in a paper in Geophysical Prospecting by Ivan Lehosky and me. And there we also include this table, which shows an overview of this modeling and how far we got today. And on the left-hand side, you have the burial domain, just schematically. And you see here going from deposition to mechanical compaction, chemical compaction, and then deeply buried and uplifted. And then you have a list of geological processes for each of these domains and geological parameters. And then you have the physical parameters, because we need to convert these geological parameters into rock physics. And then the strategy for the rock physics modeling listed here. The bold is actually where we're at. So this is still under development, and there are things we still haven't really focused too much. For example, net to gross, secondary porosity, and stuff like that. But These are things that can be added as well, of course. Also, we have been focusing mostly on granular medium models. However, if you go very deep, you could also expect some cracking, and you would have to use inclusion-based models to honor the crack porosities. Okay, so let me show you a simple synthetic example of how this works. So this is an example for an unconsolidated sand filled with oil, or actually both brine and oil. I'll just show you the difference between those two. And here we have a burial curve in the upper left, and this could be a tertiary or Paleocene sand being buried, subsiding, and then there is some uplift. But it did never reach the high enough temperatures to start frying. So it's still an unconsolidated sediment. And then you see the corresponding porosity evolution of the sand. And you see that it's quite high, starting from around 40% porosity. And then you also have the shale porosity trend during this burial history. And then you have the cement volume in the middle one here, but there is nothing because it was never deep enough to cement. And then you have the acoustic impedance for brine, but here we also apply Gasman to predict the oil in green, and then you have the shale on top. So here we see the evolution of brine sand, oil sand, and shale during this burial history, and likewise the VPVS ratios for this burial. And then you have a cross plot of acoustic impedance versus VPVS ratio for the brine and the oil sand here, showing this compaction trend. And the fluid trend, or the fluid sensitivity. In the very last plot here, instead of showing the trends, what I did now, I just include the last point, which is the present day. But then I have put in some natural variability, or what we call Monte Carlo simulation, to honor some uncertainties. So what you see here is just a spread of data, assuming some uncertainties in the input parameters. But still, you see there is a scatter, but still you see there is quite a good separation between the oil sand and the brine sand. So just doing this exercise could be a nice way to illustrate the feasibility to separate a brine sand from oil sand at a given burial history. Of course, this was an unconsolidated sand. So here we see what we call a class 3 AVO for oil, and maybe a class 2P to 2 for brine sand with a good separation. Let's try to change this burial curve just a little bit. I'm going to update it now and see it in the next one. And you see that I made it a little bit older, but also going a little bit deeper. And now it's going into this frying pan. So if you look at the third subplot, the cement volume, you see that you're starting to pick up cement. It's only a few percent, 3% cement, quartz cement. But that is one of sort of my main messages in rock physics, is that even the small amount of quartz cement, which is sometimes among geologists assumed to be insignificant amounts of cement, elastically, these small amounts can be very significant, and we need to honor them. So you see here the effect that just a little bit cement is making much higher impedances. The VPVS ratios are dropping, the fluid sensitivities are dropping, and in the AVO plot, you get different AVO classes, and there's a more overlap between when you put in some uncertainties. And you see here going back and forth how things are changing in the AVO plot here due to this increased burial and cementation, going from class 3 to more class 2P for oil here. Okay, this is another example showing exactly the same pretty much, but here in this case, I'm just showing you for a continuous subsidence. So there's no uplift, but just showing so I'm plotting discrete samples through the burial, and just see how the different properties are changing with the burial. And you see, for example, acoustic impedance is picking up when you get below 70 degrees, and the VPVS ratios are dropping, and the fluid sensitivities and the rock physics template in the lower left is reducing. And again, you see you go from AVO class 3 for hydrocarbons, green is oil and red is gas and blue is brine, and then you're getting less and less separation. So the key takeaway here is that fluid sensitivity and AVO detectability decreases drastically after you enter the chemical compaction domain. So let's go to this Glittener case example. So the Glittener field is in the southern North Sea, and this shows reflectivity map along the top reservoir horizon. It's called the top Heimdall. And what is yellow here is just reflectivities. So this is a near stack reflectivity map in yellow. And then you see 3 wells. And one of them is actually outside the map, but you can see that it's actually penetrating the feeder channel. And that was a brine or a dry well. Well 2 is actually you see some structure maps also here. So that's the top of the lobe structure, and it's encountered oil. And then you have well 3 that's just off the lobe structure in the margin, and it was brine. And you see how, and these are real AVO pics from the gathers, what you see in the AVO plots below here. And you see you go from a hard intercept reflectivity with a negative gradient, but it's not crossing the 0. So this is an AVO class 1. Then you have a class 2 to 3 with negative intercept and negative gradient, and then you're back to more class 1 again. So the question is this big drastic change only due to the fluids? Or what about this effect of diagenesis? And this is an interesting question to ask even here for a given field. And even though it's quite flat, because if you look at the next one, I included the PV velocity log from these 3 wells. Not all the wells have measured BP for the whole sequence, but you can see the message. And what's black dots or points here are shale or sandy intervals, and gray is shaly intervals. So, and I highlighted this Heimdall fan in cyan or light blue. So you see this submarine fan is at this level. And you can really see, and here I actually did this modeling, combined Valderhaug and rock physics modeling with continuous subsidence with a temperature gradient of about 35 degrees per kilometer. And you see here that the onset and the change from mechanical to chemical compaction happening. And you can really see that in the data in all the 3 wells, that you have a change in the trend. Of course, there's some variability around it related maybe to variation in clays or other heterogeneities that are occurring in the sands. But overall, there is a trend that really shows this mechanical to chemical compaction trend. And then that's interesting because there could be local changes here in this diagenesis, either related to the temperature, depth, or clay coating and grain sizes, which also controls the cement volume. So let's have a little bit further look into that. And here is from this well 2, the one in the center. I just highlight actually this zone here. And I show, and here we actually have some coarse and thin sections. So we have some information about the grain size. We even have some thin section quantification of cement volume. And you see here is actually this uppermost Heimdall units is actually 0 quartz cement. There is a little bit of other cements. And then you're picking up higher cement volume further down here in this second unit. And then you have a little bit more shale unit before it's getting more sands below again. But you can see there is a trend and change in the cement volume. And we can actually use this rock physics models to diagnose and see if you actually see the changes. And this was a technique developed by Jack Dworkin, and I worked with him also to make these constant cement models. And we see that this upper unit, unit 1, actually plots on rock physics diagnostic templates with lower cement volume, and you have an increase in cement volume to this second unit. And if you do this AVO, this modeling that I just showed, exactly doing the same as I showed you in the synthetic case, and I just modeled down continuous subsidence, I'm entering the frying pan, you start seeing picking up just at the very top, you see you're picking up the beginning of the cement. And with this, fitting it to this well, you see that the oil is predicting to be, and I put some variability around or uncertainty as well. But you see you have good separation between brine, which here will give a class 2P, and a class 2 to 3 for oil. However, if I add a little bit more cement, then that could be done in different ways, but one way is to just model it to a deeper level. And you see actually the well logs, slightly upscaled well logs are showing the same pattern, that you're increasing the impedances and decreasing the VPVS, and that's exactly what you see in your well log data. And now you see that you're expecting a class 1 AVO for brine and a 2P for oil. So just by adding cement, you can explain these drastic variations. Note also that grain size and clay coating can also play a role. So it's actually this very upper level actually had some coating in it. And it's one of the figures in my book, actually, from 2005, shows a thin section which identified this clay coating. So that could have delayed the cement volume in the very top. We're going to do a little bit scenario testing with that as well. So instead of just doing 1D, we can actually do a 2D modeling. So let's just do a scenario and a focus just over the lobe structure. And here you see the well 2 and well 3. And here I assume clay coating 0.5 means that I assume 50% of my grains are coated by clay. And they will not be cemented. So you reduce your quartz cementation. Even though we just entered the cementation window, the cement volume, and you see here to the right that the cement volume is quite low. And then you see the expected AVO class for the hydrocarbon-filled reservoir. So you go from brine to oil, and you see that you go from a class 2 to a class, or actually class 2P to a class 3, where you have the hydrocarbons. And here you see the porosities. Let's now say that you don't have any coating here, and see just, and also I'm going to reduce the grain size a little bit. Smaller grain size actually means that you have more specific surface area for cement. So the smaller grain size, usually at the given temperature or given depth, you will have slightly more cement. And that comes out from the modeling. Anyway, so I'll do that, and I go to the next one. And now you see that I changed my AVO class just by, and you see the cement volume to the right here is, yeah, it's a few percent more. It's not much more, and the porosities are slightly lower. And now my AVO classes are already flipped and quite different. And if you combine these two and make a hybrid scenario, it's actually more similar to what we see in the data. Remember, we saw a class 3 AVO in the well 2 and a class 1 in this well 3, and that's what we're predicting here now. You see that it's just demonstrating that it's a combination of the fluids and the diagenetic changes that are happening. Yeah, and I just have one figure before we move to the Barents Sea, showing also that this can be done to create some feasibility AVO attributes and compare with real data. I have one example here showing the fluid factor model from this feasibility map, and you see that here is where I expect my feasibility model fluid factor, and here is actually the observed real data from the AVO data. And you see that it's quite a good match. There's, of course, a little bit more noise in the real data, and there could be some interesting downflank anomalies that either are noise or could be further evaluated, of course. Okay, so let's move to the Barents Sea. And the Barents Sea, we're going to look more regionally, and this is an area where you have extensive uplift. And you see here some uplift maps showing in this area that you have up to 2 kilometers or even more uplift in this area. So when we do this modeling, and here's an example of this combined burial and rock physics modeling. What I do here is just a sensitivity testing of the timing, because very often we're also uncertain about when was it really buried at its maximum. If you know today that you have the present day depth, and you know maybe also you can infer from vigilant reflectance or from the seismic velocities that, yeah, these rocks have probably been 2 kilometers deeper. But then what about when was it deeper? Does that have any impact on your elastic results? And what I show here is just playing with the timing, and then you see that the cement volume, yeah, it changes a little bit. It has some impact, but it's not that drastic difference. So actually, we can assume here that the exact timing is not crucial to know. It's not insignificant, but it's more important to know the degree of burial, which is the next one. And now you see I have the same time of the max burial, but I vary the degree of maximum burial. And here is really see the impact, much more different. And you see the crossplot of BP versus porosity here, and you see that you have a bigger change between 1, 2, and 3 here. and also the AVO, gradient and intercept, you see bigger change. And of course, grain size. Here's a sensitivity test of, so you have the same burl curve, but you have 3 different grain sizes. You have fine grains and medium grain and coarse grains. And you see here that, yes, the very fine grain will be more cemented because it has more specific surface area per volume unit of the rock. Okay, so let's have a look at some real data. This is well from the Wisting area in the Hoop area in the Barents Sea. And here is comparing a burl curve and the predicted porosity, cement volume, and the velocities. And you see here you're comparing the reservoir level, the modeled burl modeling with the real data. And you can also compare it in the crossplot domain and see how it fits. And in this sense, you can assess your expected AVO signatures. And here we see also that if I just vary just a little bit the uplift here, you see that I'm switching between not entering the cementation window, the 1600. If I go a little bit deeper, a few hundred meters deeper, you're starting to cement. And that's the difference between this point and this point. But since my well log data is showing a fit with the fact that I should enter, I know that I must have entered the cementation window. However, this could be an interesting exercise if you're looking away from this well. It could be that there are nearby prospects, the same way as I showed you in the very beginning in this teaser slide, that in a prospect just nearby could have experienced no cementation. So it's important to then have some information about the uplift around that well to assess how things are changing laterally. And here's a thin section from this well showing quite low cement volumes. And you see that the expected AVO signatures is a class 2 for oil and a 2P for brine, 1 to 2P for brine. And actually, we also created a synthetic gather through this well from this Wisting field. And you see the brine response is a 2P and going to a class 2. So we have a crossover here, but not here. And exactly what we also saw in the modeling in this case. Of course, here you could also potentially have tuning and other effects affecting the AVO, expected AVO, which is not included in the feasibility modeling, but which could, of course, be included, and we're working on that. Let's move to another well in the Barents Sea where we have much more deeply buried. It's the same stratigraphic level, it's a stir formation, but it's a bit further south. And you see here that the velocities are very high, 4 kilometers per second, porosities are much lower, and here the burial history to explain this much deeper is more deeply buried today, so the uplift is actually less, but the maximum burial is larger. And here you expect an AVO class of around for 1 and very bad separation between hydrocarbons. So just to sum it up, you see here that different burial history curves will give different AVO signatures. So with that, let's look into an example where we try to look at this sort of on a basin scale away from this well. And this was a case study we did for Spirit Energy and partners in the Barents Sea license. And they were interested in some prospects in this area where I'm pointing here. This is a present day BCU. And we had some wells on the western side and we had some wells on the eastern side. And what you see here, there is some interesting structures. And we created a net erosion or uplift map from seismic velocities. So here you see the uplift map showing red is more than 2 kilometers uplift, and blue is almost no uplift. So you see the drastic changes in the uplift in this area. And then you have the maximum burial that we can estimate, combining the present day depth and the net erosion. And you see also that the maximum burial is varying quite significantly over this area. And this is the temperature during the maximum burial. And so we can now do this AVO feasibility modeling in 2D over this map. So this is showing the AVO feasibility modeling at any given location of that map. And you see here for the BCU. And here you see many curves. Each of these curves modeling the cement volume, the porosity, and the PV velocity. So this is a combined Valderhaug and rock physics modeling done at each point of this map. So you see here, and the orange dots is just showing the turning point at the maximum burial and the present day points, and then the curves in between. So you see that, yeah, there is some great variability. So how will this look then back on the map? Let's first also look at the shale trends. This is now plotted shale trends, but here I just shown them as a function of maximum burial. And this is done empirically, not model driven. So this is data driven. Each green point here represents the average value of a shale interval in one of those wells. So we see we're picking up nice trends for different shale formations. The one I'm going to focus on is actually the Fulen formation here. And you see that sometimes we wonder, should we use a linear trend or a power law trend? And you see that power law trend could maybe better explain these data, but it's also a dangerous one because when you extrapolate, it can really give wrong values if this is not really the case. It could be that this variation is more due to siltiness of facies changes within the cap rock, because the cap rock shale can also have facies changes. So at the end, we selected linear trends. Okay, so now we can create, because we have this for the sandstones and this for the shales, we can predict the elastic properties both of the cap rock acoustic impedance shown in the upper left, and here's a VPVS ratio in the upper right for the shale cap rock, and then you have the acoustic impedance for the sandstone reservoir filled with oil, and then the VPVS ratio for the sandstone filled with oil. And here I've just indicated some of the parameters that go in. We have 10% clay around the grains, constant temperature gradient of 38 degrees, the grain size is 0.3, and so on. So, and now you really see the geology coming, and this is information coming from the seismic velocities and the uplift map that we're bringing into the feasibility map. So that you can call this rock physics feasibility maps. And now when we have the rock physics properties for the cap rock and for the reservoir, we can create AVO feasibility maps. And now you see the AVO feasibility map for the brine case and for the oil case, for the stir formation over the whole Barents Sea. And you see here that if you look, and this is interesting, I think, because you see that the brine response, the AVO class for brine, blue here means class 1. You see this western area shows a class 1 for the brine, but then you move eastward, you see even the brine will show class 3 or class 4 some places. So the classes can change. So one class doesn't mean a given fluid property, okay? So, and then you fluid substitute to oil, and you see there are some interesting changes, especially in the area in between, but actually what used to be class 1 in this area mostly is class 1 also in this area. And it's because these rocks on this side are very stiff and hard, so there's very poor separation between brine and oil in this side, but on the eastern side here, you have more fluid sensitivity and better separation. So if you compare the net erosion map, you can really see how the information from the uplift map is propagating into your AVO feasibility map. So in one way, we have brought some of the geological knowledge and information into our AVO modeling, so we can extrapolate and interpolate between wells better than just doing a linear interpolation between these wells. And there's some very interesting structures going across here between these two areas. So, and here are some other examples just showing where I picked with a constant temperature. So you have the brine, oil, and gas, the upper three, with constant temperature gradient. We can also vary the temperature gradient because we can do basin modeling and account for temperature variation through in both in space and time. And this is just an example, but you see here that doesn't affect the maps too much, but there is some interesting changes in the actually in the area where the prospects were lying in between these two wells. So it is important to honor. And here we focus into this area. You see the arrow here in between, and there is a prospect, and you see that in this case we expected the brine and oil to almost have the similar property if you assume 38 degrees. But if you actually did the base modeling derived temperatures and temperature gradient varies, you actually see that you're flipping from mostly class 1 to a more class 2 to 2P domain for oil, and for gases a class 2. So illustrating the importance of having your temperatures correct. And then just I can bring it back to the crossplot here. And what I show here is a crossplot of PV velocity versus porosity for stir formation sandstone. The blue data points here are from the wells in this area, and you see they are stiffer, higher velocities, lower porosities. And the wells in the right-hand side of this map is the hoop area. They are much higher porosities and softer properties. But then I have created pseudo wells and just doing scenario testing for this prospect. And you see that I'm kind of I'm closer to the sort of this hoop area wells, but I'm starting to move in this direction. So it's slightly stiffer rocks than what I had in the hoop area. So this could be very important information to assess these area in between. Okay, so just to sum up this workflow, so what we really do, the input data is a seismic velocities. It could also be FWI velocities together with the well log data. You need some sedimentological information about sorting, grain size, whether you expect clay coating. So, and then of course the burial information. Usually that's available, but you can also do this workflow a little bit iteratively and actually use the rock physics to estimate the uplift of burial curves. But this would be an iterative approach. Or you could just, if you have a reliable burial curve or burial history, you could use that to constrain your rock physics modeling. And then you can create these uplift maps also using rock physics modeling combined with your burial curves, and then extrapolate that into the original area. And from these maps, what I showed you is to do the AVO modeling at any given location. And then you can create these intercept and gradient and any other AVO attribute. And also, of course, you can do this in 3D. I didn't show any examples of that today, but we published a paper in First Break last year also doing that. So this is, of course, this shows the importance of integration, and really to have the geologists and metallurgists and basin modeler on board and during this workflow is quite crucial to get good results. And just to sum it up then, we've shown a novel interdisciplinary methodology workflow for generation of rock property and AVO feasibilities, or CUBE, to be used in subsurface characterization and prospect de-risking. And this methodology enables rapid extrapolation of expected rock physics properties away from wells. I think also the multi-scenario modeling that we can do is a good way to assess uncertainties, or also alternative anti-models away from well control, especially in areas where you have limited well control. I've pointed on some of the key uncertainties: the temperature history, of course, the grain size, sorting, and clay volume. Of course, something that we haven't looked too much into yet is, of course, the heterogeneity and isotropy overpressure, but we'll work on that more in the future. And at the end, importantly, as I said in the last slide, realistic multi-scenario feasibility modeling really requires good integration across disciplines, and we really need to break down silos to do this. And also what I didn't show today, but is also one of the scopes that we're working on, is that we can use this as a fundament to create training data and augment training data for AVO classification and machine learning exercises. So with that, I think I would like to thank my colleagues at geoscience for their contributions, and also Spirit Energy and partners and license PL 962 in the Barents Sea for data and financial support of some of this work that was presented here. So with that, thanks a lot. I'm happy to answer any questions at the end. Thank you.
Wow, well, thanks, Per. That was pretty neat. Let's see what kind of questions we have. I'll probably have to read them to you.
Yeah.
I'm not sure you can see the screen. So the first question is from Jianbing Liang. Question: in your scenario-based models, the change is assumed to be gradual with diagenesis or sorting trends. However, in more complex scenarios, the reservoir can be very heterogeneous. For example, there can be two kinds of sandstones randomly tangled in one reservoir. They can have different textures and lithology. For example, one is a more complex sandstone and the other is more carbonate cemented. How can we model this kind of reservoir? Thanks.
Yeah, that's a very good question. Of course, here we looked at quartz cementation, which tend to be predictive in terms of depth and temperature and tends to be gradual. But of course, calcite cement or presence of some local chloride coating that could prevent quartz cementation locally within one compartment and not the other one. A little bit what I showed in the Glittener actually was that the upper compartment actually had some clay coating and the lower one didn't have it. That would also affect the lateral distribution of these. So in a sense, that was a little bit like that. But what you could think that one way to do it could be probably to include facies maps. So if there is some information from the sedimentologists that already have some interpretation of this, it could be tested with any complex model. But of course, that's kind of a chicken and the egg, because we want to try to predict or find how things look. And if this is in a frontier area with few wells, you probably don't know too much of that. But at the end of the day, you could add any complexity as you want, but of course that will create many scenarios. Combining this with an inversion workflow, maybe you could be better in terms of classifying different facies and then use that again and sort of iteratively do inversion and AVO feasibility modeling. Maybe that's a way as well. So yeah, thanks.
Yeah, thanks. Yep. I had a kind of a similar question like that. So the what different regimes have you been working on besides these? These are kind of large, smooth, we'll call them smooth structures, et cetera, but have you done anything very compartmented, studies like that?
Yes, we did a study for a company in Canada recently that we plan to present at the EAG workshop in the fall, which was quite complex in terms of the burial history offshore Newfoundland.
Yeah.
And and then of course locally also we've been testing out more the 1D scenario, of course, but also playing it in the sort of a near field, for example, in the Horda platform, where you go from one compartment to another. And one way could be, for example, to assess, is the flat spot you see a fluid, or could it be a diagenetic contact? And actually, sometimes we actually use this technique to identify the genetic quartz. The onset of the cement was actually creating a contact, which we actually could model in advance before, and it turned out it was yeah. So, and also there in the Tampa Bay area also been testing it out. So they've been using it locally, but more in a 1D sense. But this 2D assessment, there was one example I had maybe some I think I have a backup slide here that shows a study with PGS that was published in First Break, which is also quite complex in terms of the compartments in sea here, for example. And this was an area where these maps were created just before a well was drilled through here. And you see drastic changes between the compartments, where you see the upper right here, you see unconsolidated, no cement in some of them, and then you see more heavily cemented compartments, and part of this is deeper, of course. You see it's almost no porosity, and then you see the corresponding AVO, expected AVOs here. So this is an example where it was used in quite heavily, but of course with very limited well constraints. But still, it was interesting to see that. I haven't had the time, because there was actually well drilled inside this volume that I would like to compare with these results, because that's more like a blind test. Yeah.
Okay, and what's like? You definitely, I'm assuming you need information from the, like say, from the seismic in terms of the velocities going from well to well and stuff like that. How have you done, feasibility studies? Where you put in an error bar, assuming that there's this much error, that like you have FWI, or you have some older stacking velocities, et cetera, et cetera. So how big of an impact is that on this?
Yeah, actually, in this example I show here, we actually use FWI velocities, and you see that you could actually constrain this AVO visibility in 3D, and you see it picking up details here. So you see
Yeah.
here the velocity. So actually, that gives even better results than what we did with the Spirit, where we used just conventional stacking velocities or interval velocities from stacking velocities. So that was a big improvement. You see details in the uplift map here that is quite more detailed, huh? So yeah, but of course there are uncertainties with FWIs, and when you start adding uncertainties and trying to quantify that, it will propagate, and at the end of the day, you will probably have error bars that are just too big. So, but of course, so that's how I think this, and we are working now to see how we can best present the uncertainties associated with the feasibility maps. And now doing this, we can do it more very automatic. So we can create maybe 100 scenarios or 1,000 scenarios and just play with some of these parameters. And one way we address, we actually, for the Canadian study, what we suggested there was actually to put P10, P50, and P90, and then make some realistic variations in the input parameters, and then see how that propagated into sort of pessimistic, realistic, and optimistic cases.
Yeah. Well, there's a similar question from John Coughlin, who's asking, what about outside of North Sea, Barents Sea, where there's less core advanced log data? How do you handle this uncertainty, which is similar to what you're talking about here?
Yeah, I think the whole idea why we started with this technology is because in the Barents Sea there is quite complex geology, and actually only a little bit more than 100 wells drilled, whereas in the North Sea it's like 6,000 wells. So we really needed to have model-driven approach to extrapolate between or to away from wells. And the same thing was also for the Canadian study, huge areas with just a few limited wells. And that's kind of the advantage, I think, with the way we're thinking, is that geological knowledge and information from the seismic velocities contain geological information that you want to bring into your feasibility modeling. So in a sense, yeah, there are big uncertainties, but I would say they are smaller than not including this information at all.
Yeah. Good.
Yeah.
There's another question. Oh, well, okay. What's your opinion on viscoelastic property, I guess, and how that impacts you would be the question.
Yeah, well, it's of course on the fluids. It can, in terms of absorption and attenuation, it's when I work with AVO data, usually I've been working on data that has been Q compensated, so that attenuation effect should have been taken into account, so it's not distorting your AVO responses. Of course, you could think there has been a lot of work also trying to include. I think Chapman in Edinburgh and others have looked into how you can actually do frequency versus offset and make AVO attributes that actually contain the frequency information. And that's a promising way to go as well. And you could think that maybe we could create AVO visibility maps that also included attenuation. I think before we go to sort of the viscoelastic, I'll rather start looking at more the heterogeneity, whether it's probably going to induce some scattering attenuation, of course, but also just a net to gross issue. I think that's sort of number one on my list to add here in this workflow, tuning and net to gross. Yeah.
Yeah, I did see, yeah, I was thinking about tuning, you brought that up earlier. Of course, if people are trying to do their own, inversion that's attempting to strip out the tuning, then, you invert the seismic. So at the moment, what you're providing is something that assumes there's no tuning, right? I mean, the product that you're showing here. Yeah. So, yep, these are things to keep working on for sure.
Yeah.
Yes.
Yeah, we're actually just starting this month a research project where we're extending this with support from some local companies in Norway. and one of the key focuses is actually to put in the thickness of prospects, or so we actually also can do AVO feasibility, where the tuning and thickness of your reservoir. So not just putting the top surface, but actually the expected thickness as well.
Okay, yeah, great. So Ben Ruck just asked that, like, how would you incorporate that in your modeling, the tuning? But I guess we'll have to wait and see.
Yeah, so that is probably yeah. So it's but it's, I mean, there's the equations for it. It's quite simple. It's just that yeah, so it's just to include, it's more to get the geological interpretation of those thicknesses from the sort of stratigraphic interpretation, and how you implement that. I think it's, yeah.
Okay.
Another thing that I could add is, of course, also to use this as a way to assess source rock maturity and stuff like that. That's something we also want to work a little bit on. Knowing that the source rock and how they mature will affect the rock physics properties, and that's really depending on the temperature and burial history. So, yeah.
Pretty cool. Let's see. Let's see if there are any more questions. I think we've covered them all. Very cool course. Just to remind people that on YouTube, this will be out on. You just search for ASEG, and within a week or so, this will pop out there, and maybe they can edit out my speaking and just have the good stuff. But we'll see. In the meantime, I'd like to thank her once again, and unless anybody has any more questions, I think maybe it's time to let you relax, and everybody else in Perth to get ready for dinner, and people in Sydney finish their dinner, I guess. Okay, well, thanks a lot. Really appreciate it.
Thank you. It was a pleasure to present today. Thanks a lot.
Great. Thanks. Okay, enjoy it up there. Cheers.
Thank you.
Okay, bye.
Bye.